Good morning, good afternoon, and good evening, everyone. So, today we're going to be continuing our linear algebra series, and we're going to be talking about conceptual problems for my homework, basically. Okay, so here we're going to cover some problems on sections 3.1 to 3.3. So, these are about linear transformations. Then we also have something about matrix algebra. I can't see my screen. Algebra. And then we also have inverses. Okay. Right. So let's talk about them real quick. So we're going to start off with this problem here. So here we see a linear transformation T from R3 to R2. And then we have this S transformation from R2 to R4. And so when we do a composition of linear transformations, it's going to be from R3 to R4, right? So we say the S of T would be R2 or R3 going to R2 going to R4. So R3 going to R4 to shorten it out. Okay. Now the question, can S of T be one-to-one? Now what does it mean for a linear transformation to be one-to-one again? So to be one-to-one, we have a couple of things that we can consider, right? If we turn it into a matrix, so turning it to a matrix or a matvec matrix in echelon form should have pivots or a pivot every row. And so it should span R4. Right? Those two IDs are just to connect together. What's another thing we can check? Actually, that's it. For one-to-one, that's all we can check. Oh, shoot. No. My bad. I was talking about onto. I mean every column. So column vectors. We're not talking about the vectors. We're talking about the set of column vectors is independent or linearly independent. Okay, that's what we can think about doing. So we're going to, the hint is to start thinking about all x such that t of x is 0. So let's start thinking about this logically. If t of x is 0, another way of writing it would be t x sub 1, x sub 2, x sub 3, because we have 3 things. This is going to equal a vector of 2. Now, is there a way to make this possible? Is R3 to R2 possible? I mean, it is if we have a matrix 2 by 3, right? Because we just reverse it. We should be able to get this. But the question we're asking is if S of t can be 1 to 1. So t of x is the same thing as ax equals 0, such that a would be a, b, c, d, e, f, right? Okay, what else can we say? I don't think I'm getting anywhere here. Mm. Oh, look at that. Looking at this vector, looking at this matrix, can this have a pivot every column? No. Actually, we do this. This one's easier. Let me write it this way. A11, A12, A13, A21, A22, A23. If A, B, such that A11 tilde, A12 tilde, A13 tilde, 0, A22 tilde, A23 tilde. This is in echelon form. There is no pivot every column. So T is not 1 to 1. Okay? And now going back to that idea, going to S of T, which goes from R3. Oh no, S goes from R2 to R4. So we take in okay, S of T of X is equal to 0. No, is equal to S of 0. Can this be possible? Oh, no, no, no. Actually, that's not the way to do it. If D is not... I think it wants us to say something about a homogeneous linear system. I think that's what it wants us to say. Because here we can see there is going to be a free variable. If we equate this to 0, right? There's going to be a free variable here. And so this is a dependent set of vectors. And so it's not 1 to 1. And if T is not 1 to 1, then S of T is also not 1 to 1. I think that's how it wants us to explain this idea. But we can check. Okay, there has more choosing on 0 vector. D is not 0. Because it has more variables than equations. Yeah, so it has more variables than equations. Let me choose a non-zero vector V in R3. 0. Oh, but V is not zero. It's not a non-zero. It's not a zero vector. Okay. I mean, as long as we explain it, we should be good. Okay. The purpose of this is to really explain how things work. Okay. Not so much about the math behind it. It's really about explaining it. Okay, here we find a 2 by 2 matrix A. This is not zero nor identity, satisfying each of the following equations. A squared equals zero. So that's after 3.2, after we get this idea of matrix algebra. So let's try it out. Well, A squared, if we want this to be a zero and it's not identity, we have to multiply two matrices together that would give a zero matrix. What would that be? And they have to be the same. Huh. Hmm. I could try something. I could guess it, right? I could do one, one, then here would be a 1. So 1 times 1, 1 minus 1. That would give me a 0. So that checks it out. It's also a 1. How about this? Negative 1, so this must be a positive 1. Oh, shoot. My bad. This is supposed to be a negative then. Yeah, because if I multiply this by 1, so it gives me a negative 1 plus 1 gives me a 0. Then I keep going. 1. Yeah. So A has to be this one. So A squared is this. That would give me a 0, right? It's from practice. Okay, that's A. How about A squared equals A? Holy moly. What would that be? A 0 or identity? Hmm. Well, here I would just guess it, right? I would say there has to be something that we can square and we would still get A. If I do, I want to make A 1, 1, 1, 1. How do I do that? How do we do 1, 1, 0, 0? Can we, let's see. 1 times 1 is 1, plus 0 is 1. All of these are zeros. All of these are zeros as well. This. Oh, and there we have it. So A would be that. So ways to just guess it and check. And there are probably some other ways to figure this one out. Well, if we do A squared is the identity squared. Or when we say identity, it's just 1, 1, 0, 0. How do I get that? And note shouldn't be the identity nor a zero matrix. I would try 1. 1 times 1 is 1. And then maybe a 0 here. This one turns out to be a 0 too. Actually, I could do. Here's what I could do. I could do. hmm, This one could now be a 0. Then this would be a 1. This one works. 1. This one gives me a 1. Now if I go down, both of them should give me a 0. This one should give me a 1, however, though. So this and this should give me a 1. I would say this is a 1. Let's try this one. Let me see. We try this. That gives me a 1. That checks it out. Try this next one. 0 times 1, 1 times 0. That also works. Let's try this next one. Times 1. Well, that one gives me a 1. We need to somehow make one of them a 0. Uh-oh. See, this is where my guessing game starts to fail. Well, we do negatives. If I do this, just reverse it. This should give me the same thing. 0 times 0, 1 times 1, that gives me 1. 1 times 0 times 1, that gives me 0. 0 times 1, 1 times 0, that gives me 0. 1 times... Okay, this one works. There's no identity. It's also not 0. So I think this one works. In my other class, and I think we've discussed this is not related to this class, but this is what we call a permutation matrix. Because we switched 1 with 2. And we multiplied it by the same thing. And so we should get back the identity. Okay? So it's just a neat trick that somehow works when you just switch the rows together. Okay, this is I2. Cool, done. There are some ideas on how to go about this. Okay, here I think these are interesting ones. Just because it's hard to figure it out. Okay? Let's try this one. Here we're being asked to find a linear transformation such that the linear transformation reflects a vector about the x2. So what is that linear transformation? If we want this thing, this vector here, to reflect about the x2 axis. So when we have x sub 1 somewhere, x sub 2 somewhere, we have a vector that reflects it. Well, we just want to make this thing a negative. Or one of them a negative at least. So when we have, let's say this is the equation x squared equals x1. Now the way to reflect this is to just switch it around. So we say negative x1 equals x2. So it's actually just making any one of them. Yeah, we just make one of them negative and we should be good. We just make the x2. Mhm. this thing should become x sub 1, x sub 2. So when we think about our linear transformation, there has to be a way to multiply this, and that a is going to be something. We just do this. And this should give me a vector. Okay. So a should be this guy. Right. We're just reflecting it across the x sub 2 axis, or in this case, y. And so the way to do that is to make x sub 1 negative. Now, if we want to reflect across the x sub 1 axis, you would make x sub 2 negative. Okay? All right, let's try this one. I personally think this one's pretty interesting. Here, we want to find a linear transformation, R2 to R2, such that this thing rotates a vector, x sub 1, x sub 2, counterclockwise by 135 degrees. Okay. How do we do that? Huh. So if we try basic vectors, and if we rotate them counterclockwise by 135 degrees, what would that be? So this one, we need to somehow get the intuition for it. So let's not talk about transformations first. Let's talk about pre-calculus. So say we have this line here. Okay, fine. We know this is the vector 1, 0. But then if we were to rotate this 135 counterclockwise, so it's going to go this way. How do we do that and make it 135? Well, it's going to go this way, right? And then this one would be 135 degrees of rotation. But now, what is that vector going to be? Well, that, if let's say this was 1 and 0, that would be this thing is going to be cosine of 135 and sine of 135, which is actually a pretty nice idea here, right? Now, my only issue is I don't know how the hell to get that number. Okay. Or in other words, this thing tells me it would go to what? Negative square root of 2 over 2. And so this must mean this is square root of 2 over 2. Sine of 135. Yeah, because that was the positive version. Okay. So when we rotate this vector here, we say this is 1, 0, or this ordered pair, this point, we would get this. Okay. We can think of them as vectors at the end of the day. So in general, what are we doing here? We are rotating x sub 1 and x sub 2 by these guys. Anyways, let's think about that. So this one would go, so it's really just removing a bunch of things around. Would go to that. And then maybe another idea is 0, 1. Where would that go? So 0, 1 starts from here. Or no, 0, 1 starts from, whoops, starts from here. Rotating it counterclockwise would be all the way over here. Then that's also a 135-degree angular rotation. But then how do we get that? Well, I would just multiply, right? Now that thing would give me, hmm, actually would give me both a negative. Okay, that's the intuition behind it. This thing is also a 135-degree angular rotation of the vector, the green vector. This one's the blue vector. So t of x is equal to b of x, where b is just, so it starts off from that vector 1, 0. That 1, 0 is going to go to where? The negative square root 2 over 2, square root 2 over 2. And then 0, 1 is going to go where to where? Negative 2 over 2, negative 2 over 2. Okay. And so maybe just to make it nice, we can do this. Or we factor out this 1/2. So it looks like a scalar multiplication of a scalar to a matrix now. Okay? So this thing is what we would multiply this x function to get its rotation by 135 degrees, given any vector. So this for all x. Okay? So this should be the answer. Okay, let's look at something else. Uh-oh. Huh. Okay, we have a couple more. Mm, oh, shit. Okay, let's saw this one. Here we're being asked to find a linear transformation U with domain and codomain that has the effect of first reflecting as in A and then rotating as in B. And then we give the matrix of this transformation explicitly. And how is this transformation related to T and S? So again, what is domain and codomain again? Well, if we look at our section, because I also forgot, I haven't seen that one in a while. It's probably here. It's one of the basics of a linear transformation. I think it might be the first thing we look at. Okay, the domain is the input vectors, while the codomain are the output vectors. That's what it is. So given some linear transformation, is going to have the domain, which are the input vectors in Rm, and codomain, which are the output vectors in Rn. That's what it is. Then for every vector of u in Rm, the vector t of u, because we're transforming it, it's just going to give us another vector at the end of the day, is just the image of u under t. And then the set of all of those, so the set of all of those t u's, sub j's, I don't even know how you would call them, but it's all of these images of u under t, that's going to be the range of t. Okay? I can't do my eraser. Okay, but it's going to give us this, right? So again, just to briefly recap what I'm talking about, the domain in this case. So given t goes from Rm to n, domain is basically the input vectors that belong in Rm, and codomain is the output vectors that belong in Rn. Then we have t of some of these input vectors, and we call these images of input vectors under t. And then we also have the set of the input vectors. So the set of images of input vectors under t. And we would call this the range of t. Okay? And so we say range of t is a subset of codomain of t. Yeah. Right. So those are definitions that might help us answer this question. So again, we find a linear transformation U with domain and codomain that has the effect of first reflecting and then rotating. So you want to reflect first and then rotate. So actually, we're just combining the thing out of this one. So we say we want to reflect first, right? So we want U of X. This is equal to, first what's the transformation that's reflecting? It's this T vector. This one is S, my bad. Oh, I wrote T. Because it says T, which is weird. So here we want S of T of X, right? Reason being, we want to reflect first, so we use that T transformation to do so. And then we use this S transformation to reflect it. Now we actually already have a nice idea for this. And that one we can solve, which is BA. Now BA is just the matrix B, negative, so that one, so it's actually easy. So this is that thing for reflecting. And then we're going to multiply to a matrix that's, no, this is the thing that's rotating it. And then we need the thing that's reflecting it, the matrix. So that one's going to be negative 1, 0, 0, 1. And this works because the number of columns of B is equal to the number of rows of A. And so we get a matrix out of that. Now it's still going to be a 2 by 2. So actually, this would give me a nice one. I'm going to do it scalar. So this is a half square root 2 minus square root 2. And then minus square root 2 minus square root 2. And we have it. Now that thing right there, and then we just multiply it by our vectors, we would get the u function. So it's really a cool way to store things like these. Okay. So u is a composition of t followed by s. And then it's the same idea. Oh shoot, wait a minute. Oh, okay. Okay, this is where I think I messed this one up. Because then I was thinking of rotating it back, which doesn't make any sense. So the thing about this one, we want to find a matrix representing the linear transformation that first rotates and then reflects and then rotates backwards. So that is something. So we want to find matrix C that rotates. So what's the thing that rotates? That rotates, I think the one that rotates is the B one. So B matrix. Then reflects. So this is, I think, the A matrix. Then rotates backwards. So now this is clockwise. And actually, it's just the B inverse. After 3.3. This is just actually the B inverse matrix. So putting it all together, we want this thing. Wait a minute. So rotating clockwise by 135 degrees is the inverse of the linear transformation S. So it's the inverse of this thing. So we want to get the inverse of V. So it first rotates and then reflects and then rotates backwards. So actually, oh, my bad. First, it's going to rotate. So we do the inverse first. And then it's going to reflect as an A. And then we're going to rotate backwards. And there's a nice way to get this B inverse. We just use a quick formula to get it. But then, yeah, we're going to get a C matrix out of it. And I'm not going to solve for that anymore. And then B inverse, I'm not going to solve for that anymore because we already know what that is. We can just use a quick formula to get it. Okay, what matrix do you get if you repeat the sequence in part D 10 times? Huh. How would that work? Okay, actually, wait a minute. For D, First rotates as in B. But why are we making it inverse first? Reflects as in A and rotates backwards. What? Hmm. The funny thing is when we're actually doing matrix multiplication, we're actually applying a transformation to a vector. That's the funny thing. I'm asking ChatGPT how this works. Hmm. We rotate. Oh, shoot. I forgot. Yeah, the order was so first it rotates, and the order is that we're going back. So at first, so first it rotates, so B, and then it reflects, and then it rotates backwards to B inverse. Wait, is that the right answer? Okay, I have to rewatch this video. I don't know how I thought about it, but it's this backwards idea. Because we think of it like functions at the end of the day, right? Anyways, okay. Let's let's try this next one. So what matrix do you get if you repeat the sequence in part D 10 times? I don't know. We'll see. What happens if we repeat the sequence in part D 10 times? So if we keep doing this, and we want to write it in terms of A and B. So we're gonna get this thing to all to the power of 10, right? That's what we're doing. And apparently, well, we could do it by hand, but I'm not doing that by hand. I would just do a computer code to do this. But we would actually just get B inverse, A to the 10, and B. Okay? Now, I think the best way to do this is to first identify a pattern, if I'm not mistaken. I think, yes, we would have to represent some pattern here. Oh, wait a minute. Why is this? You would end up with identity? Seriously? Oh, shoot. Okay. Yeah, that one's a complete mess up. This one, yeah. So we have B to the negative 1, A to the 10, and then B. Hmm. Wait, I'm curious. What happens if we multiply an inverse by an inverse? But it still result in the same thing. Oh, I see what's going on here. I don't get this B though. I mean, one way to just check is to literally write it out. Yeah, it's one of these times where I'm just confused with what in the world they're asking me to do. Matrix conjunction. Yeah, I would try to find a pattern at some point. Oh, so it is. Okay, wait, let me see. Let's do a few terms. So say we have, let's do 2, right? What's that going to be? That's B negative 1 AB. B negative 1 AB. And what's that going to look like? Well, that's I would just straight up multiply all of these stuff. We're going to do associative, right? So we could do this. And then we multiply this thing first. And that would give us an identity, right? This one would give us an identity. A, B. Okay, I see it. And then B inverse is just A, B. And then this one is just A squared B. So in general, we say that this thing, based off of what we just saw, all the way to some n is equal to B negative 1 AN B. Therefore, when we multiply it by a 10, A10. Okay, nice. Okay, and we're gonna get something out of this. And funny enough, and I think this one is not super obvious to me, but it's actually gonna just give us the identity. But we're just writing it in terms of A and B. Okay. Okay. Let's find all the values of x. Yeah. Hmm. Let's see. Oh no, this is the last one. Yeah, okay, this one's gonna be. I feel like I'm dozing off. This is gonna be the last one. I'm gonna take a short break afterwards. So here we're being asked to find all values of x, which the matrix doesn't have an inverse. How do we know if a matrix has an inverse? So again, we look back at our definitions. So one is square matrix. Second is its linear transformation is both 1-to-1 and onto. So this is a square matrix. You can already see that. This is also, so you can already see matrix is square. We just need to check if it's one-to-one and onto. How do we do that? We could do Gaussian elimination. And somehow get this to echelon form. And then we check if there are pivots in every row and every column. And if it does, then we know that this thing is indeed, it will have an inverse. And so, oh shoot, what the? Compute the inverse by appending an identity at the end. Wait, why do we need to do that? Oh, because we're computing for the inverse. Okay, okay, okay. Here's the thing. We don't need to find the actual inverse. We just need to know if there is an inverse, right? So the way I did it was I literally just computed it and got the row echelon right here. So when its rows are linearly dependent, which means that one row can be written as a combination of the others. What does this mean when its rows are linearly dependent? When we look at their rows, and let's say it's an echelon form. So let's look at this one. When they are literally, we can write a linear combination of one of the rows to the other. We can think of them as row vectors in this case, right? Because we can think of matrices as row vectors. Okay, let's try going for a different definition. Let's go with the one I know. Okay, let's reduce this guy. So how I would do it, well, did he make it in reduced? Oh, he did. Okay, he actually did. He made it reduced. So I'm just gonna copy what he just did. 103 0 1 10 0 0 7 minus 10x. Because what my professor did was he or she, what she did was she did an augmented matrix like in our previous video, and she found the matrix, the inverse matrix, which we don't need to do, right? We just need to determine. That's not what the question is asking. The question is asking what are the values of x which the matrix does not have an inverse. So here we have it in row echelon, right? It has to have a pivot in every row and every column so that it's one-to-one and onto, and it's square. So have a pivot every column and row. We need this thing, this term here, to not be a zero. That's it. And so going about that, we need this to not be 10x. X shouldn't be 7 over 10. So that matrix has an inverse. For not, oh, okay, does not have an inverse. So that matrix has an inverse. So x should be 7 over 10. So that matrix does not have an inverse. It's really this simple. You don't have to do a bunch of complicated stuff. We just look at our definitions and we answer it based on what we know. Anyways, I hope you guys enjoyed that video, and I'll see you all in the next one.